Hi everyone, this is Mr. Lee. In this video, we're going to go over distance, displacement, speed, and velocity. Alright, so we're going to start off with a couple of definitions. Remember, at any point in the video, make sure you pause the video, copy down any important information, and if you're trying to solve an example problem, make sure you try to solve it on your own before you see how I approach it. Okay, so a couple of definitions to start off. The first one is distance. So distance is just how far something has traveled in total. Okay, nothing fancy about that. The next one, displacement, you'll notice I started because displacement is a terminology that we'll be using throughout the entire year in its many forms. So displacement is the object's change in position, and here's the important thing. It only tells us how far the object is only from the start of the journey to where it ended, and the kicker, the direction. So the direction does matter. And as a reminder from the previous notes, anytime we have something that deals with direction, this is what we call a vector. All right, next up we have speed. Speed is how fast something has traveled, and speed is a scalar. It doesn't care about the direction, much like the speedometer in your car. It doesn't tell you what direction you're traveling, but how fast you're moving. And the last one is velocity. So velocity is just like speed with a couple of little caveats. Okay, so velocity only cares about the start of your journey and where you ended up. Okay, it doesn't care about all the things in the middle. And it is also a vector, so the direction matters. So that's a big difference between speed and velocity. Speed just tells you how fast you're moving. Velocity tells you how fast you're moving and the direction that you're moving. Okay, so with that, we have a couple of variables, units, and formulas. Let's just go over this individually. The first one is delta, and you'll notice that delta is just a little triangle, and this is the first of many Greek letters that we'll use. So this triangle, there's no units associated with it. It tells us what the variable that comes after it, it's basically a formula. Okay, so we'll see an example where delta is used, but basically the formula is delta tells us we're looking at the final minus the initial. So it's the difference between the two. Distance, lowercase d, and the units are lowercase m. In physics, we always use meters to tell us how far something has gone. We do not use feet, we do not use miles, we use meters and its different derivations, such as centimeters or kilometers, but we never use miles, feet, or yards. Alright, so with displacement, now we can see that delta coming up. Displacement is delta x, and as a reminder, down here we can see that x represents position. Okay, so displacement is the change in position. So we can see that this delta here tells us that we're looking at the final position minus the initial position. So this O right there, that 0, mathematically, I believe it's called naught, N-A-U-G-H-T, but it's another way for us to look at the initial or the start. Sometimes instead of XO, you might see me write it as XI, where that I does stand for initial. Okay, so because this is the first of many formulas that we'll go over, make sure you, if you have a highlighter handy, highlight that. If you don't have a highlighter, you can box that. All right, time, just T. And the units that we use are seconds. You are expected to know that there are 60 seconds in 1 minute. In 1 hour, there are 60 minutes, and therefore in 1 hour, you have 3,600 seconds. Okay, jot that down. All right. Next up, we have speed. So the variable for speed is the lowercase s, and the units are meters per second. So speed is actually a ratio of how far you travel in the amount of time. And the formula here is speed is equal to distance divided by time. Next up, we have velocity. Okay, velocity, the units are still the same, meters per second, with a lowercase v. Now, on the formula sheet, because velocity is a vector, you will see an arrow right on top of the v, but for us just practicing problems and just going over the notes, you'll see me often omit the arrow on top. All right, now we have this giant formula. We won't always be using this giant formula. In fact, I'm going to highlight the formula that we'll be using a lot in class, and that is just because it is known what that delta x represents. So that delta x pops up again, and as a reminder, delta x, this is your displacement. So velocity is the displacement divided by the frame of time that the displacement took place. Okay, so the official formula is this giant formula here. However, when we do our practice problems, you'll often be only using the part that is highlighted. All right, so there we have the different formulas, the variables that we use for formulas in the units. Just as a side note, it's important that you always have units that's associated with your final answer, or when we're doing labs, the units does tell us a lot about the numbers that you are collecting and using. Okay, so the phrase is never have naked numbers, and what that means is your numbers should always have units associated with it. Now, when you're doing your math work, it's not often necessary, but for everywhere else, please have your units. Okay, so with those formulas, let's go over a couple of practice problems. So as a reminder, if you want to, feel free to do so, but definitely pause the video here, jot down the example, try it out yourself after I go through the explanation, and see if your answer matches mine. And that would be a great time if you have a calculator to bring out a calculator to perform these calculations. All right. So highlighted there, you'll see the words I and guess, right, written in a vertical fashion. This is just a problem-solving technique that we use in physics. And without me saying it out loud, this is the problem-solving technique that I approach for every single problem that we do. So I'll guide us through, I guess, as we solve this problem. So we have a car that starts from a position of -3 meters. It drives 10 meters to the right so that they end at the 7-meter mark. Then they drive 4 meters to the left. I want you to determine the total distance and the displacement. All right, so I is the image. A lot of times physics problems will give you the image associated with the problem, but if they don't, that means they are requiring you to practice the skill of taking something that is in written form and creating an image from it. So I'm going to create a number line to start off. So this is my number line. I made it nice and big. Here is my 0 mark. Now with your sketch, it doesn't have to be very artistic. Just have enough detail that matches the prompt. Okay, so we start off at the -3 meter. So let's see, we have 1, 2, 3. So we are starting at the -3 meter, and I'm not going to draw the car itself. I'm just going to represent the car as this dot right there, and they drive 10 meters to the right, so they end up at the 7-meter mark. So 1, 2, 3, 4, 5, 6, 7. Okay. Notice here, I'm putting down the important information. These are what we call the givens that are part of the sketch. And because we went from -3 meters to the 7-meter, what should I do? I'm going to include a vector. Okay, so we are going to be trying to solve this using the tip-to-tail method along with the mathematical formula method. All right, so we ended up at the 7-meter mark, and then they drive 4 meters to the left. So 4 meters to the left from 7, we have 1, 2, 3, 4. I'm going to draw this vector right on top, and I'll do this in a different color so you can see the difference. 1, 2, 3, 4, boom, and this is our final position right here. Okay, so we got the eye done, right? This is the image. So let's just identify the givens. In this image here, I have almost all of the givens except I don't have that -3 there. And you know what? I can even write this is my start, and right here, this is my finish. Okay, unknowns. Now this one might take a little bit of practice getting used to. When we do a lot of physics problems, we're usually solving for one unknown variable, and it's important to know what you're actually solving for. So in this case, we're looking for the total distance and the displacement, right? So my method of doing this is I just like to write the variable, so distance, question mark, and displacement. Question mark. So the act of you just writing it out by hand helps you organize your thoughts, especially when the formulas get a little bit crazier. Okay, and so boom, unknown's done. Now the equations. All right, so for this unit, I know that we're solving for distance and displacement. Okay, so for displacement, we know that the formula is delta x is x final minus x initial. Okay, and distance is the total distance, so there's no real formula for that, but we will be able to solve for that. And now we can do the substitution. Okay, so to find the displacement, our initial position, we have that as -3. Okay, and our final position, we can see from our drawing, we have 1, 2, 3 there. All right, so this here, this line there is a minus sign, and now we did our substitution. Now we can solve it. So 3 minus -3, this simply gives us a total of +6. And remember, no naked numbers, have your units there. M for meters. Okay, so hopefully you got that one. Whoops. If not, you just saw exactly the steps that I would take to solve it. All right, now if we were to look at this with the tip to tail method, okay, I'm gonna do this in, let's use the Galaxy ink, right? My first vector here is the long bottom one, and my secondary vector is the shorter one pointing to the left. So the tip to tail method, you put your dots or the start of your arrow, okay, at your initial position, and you go towards wherever you ended. So I ended right here, so I can see that my displacement is at the 1, 2, 3 meter mark. Okay, so I solved it using the mathematical method here, and I used the tip to tail method above. Okay, so all happy. All right, now let's solve it for the distance. Distance is just the total sum of everything that you traveled. So the first length of travel was 10 meters, and then we traveled a total of 4 meters. Okay, so it'll just be a total distance of 14 meters. All right, let's do the same thing with the next problem. Okay, once again, I encourage you to try this on your own before you see what I do. All right, so this part of the problem says the journey took a total of 2 seconds. Determine the speed and the velocity. So this is like a part 2 to the first problem. All right, we already have the image. We already have the givens. I'm going to rewrite the unknowns. So S is equal to question mark, and V is the question mark. Okay, and right underneath of that, I'm going to write down the equation. So speed is total distance over time, and velocity is your displacement per the interval of time. So we have the equation, and now let's do the substitution. So we know that for speed, the total distance that we traveled from the previous part, we saw it was 14 meters. Okay, oops, I didn't write the givens here. So let's write that givens there. I put a check mark when I shouldn't have. So 14 divided by the 2 seconds, our speed is 7 meters per second. Once again, no naked numbers. Make sure your answers have a unit. All right, now let's do the same for velocity. Our displacement, I believe it was 6 meters. So we have 6 meters, and our time was also 2 seconds. So our velocity, lo and behold, 6 divided by 2, this gives us 3 meters per second. Now, because velocity is a vector, it's important that we have a direction. Now, right here, it's omitted, but there is technically a positive there. So that positive is our direction, but we know that from our image, we can also put down the word right, and all of those cases makes this a vector because it has both magnitude and direction, and we will be very correct. So we can see here that the speed is in fact bigger than the velocity, okay, because velocity only cares about the start to the end, but the speed cares about the entire distance itself. All right, let's do a secondary example. We have a ball that is thrown upwards. The ball reaches its peak of 4 meters in 8 seconds before it starts to come down in the same amount of time. So I don't have the I guess method written down, but you can see how I approach this problem using the I guess method. So I'm going to do a first my image. So here's my ball. My ball is going to go up, right? And I'm going to label this here. Okay, this is this took 8 seconds, so these are my givens, and this time, or this distance that it traveled here, would be 4 meters, right? And then after that, it went from here, and then it fell back down, right? So because this is my sketch, right, it's just really important for you to know what's going on. Usually when there's like a passage of time, I put like a little note there, But for the sake here, I think this is fine enough. And we know that by the time it reached the floor, this is a total of 16 seconds, and it traveled a total of 4 meters going down. All right, now here's a part about the physics where there's a lot of the physics that is not given directly in the problem, but is like assumed, and it is a given, right? So one of the assumptions is that right here, that floor, I'm going to call this position 0 meters. Okay, so it went up a total of 4 meters and it fell down a total of 4 meters, but every time it left the floor and it returned to the floor, it returned and did all that starting from the 0 meter mark. Okay, so let's put a little star next to this one because this is one of our first of many givens. All right, now let's write down the thing that we're looking for, right? Distance, displacement, speed, and velocity. All right, always a good habit to keep in mind what we're solving for, and let's solve for these individually. Let's do distance first. Let's do distance here. So distance is just the total distance going up and down. So it went up 4 and it went down 4 for a total of 8 meters. Boom. All right, displacement. So displacement is final minus initial position. I highly encourage you to be writing the formula as your very first step, because with AP Physics, what we will very quickly do is we're going to be solving these problems without numbers, and we'll just be solving in variable form. So having the initial formula there really does help. So delta x, our final position is 0, and your initial position is also 0. So it looks like your displacement is just 0 meters. Ooh, interesting, right? There we go. Now speed. Speed is your total distance divided by your time. Our total distance was 8 meters, and our time, let's see, it took a total of 16 seconds. So 8 divided by 16, this is 0.5 meters per second. And then finally, our velocity. Our velocity is the displacement over time. Our displacement is 0 meters and our time is 16 seconds. Therefore, our velocity is a big fact, 0 meters per second. All right. And that's that for this video. Okay, I'll see you next time. Bye-bye.